Hello students, let's revise the chapter Magnetic Effects of Current with two case study questions in this video. I hope that this video will help you a lot for the term 2 revision. So shall we move on with the questions? First question, we know that current is due to the charges in motion. Thus, it is clear that a charge moving in a magnetic field experiences a force except when it is moving in a direction parallel to it. If the direction of motion is perpendicular to the direction of magnetic field, the magnitude of force experienced depend on the charge, velocity, strength of the magnetic field and sign of the angle between V and B. Direction of magnetic force is given by Fleming's left-hand rule. Let's go to the first question. If an electron is traveling horizontally towards east, a magnetic field in vertically downward direction exerts a force on the electron along which direction? So let's know that first these are the four directions: north, south, east and west. So the magnetic field is pointing vertically in the downward direction. Now the electron is traveling horizontally towards east. Let's understand that the direction of current is always opposite to the direction of motion of the electron. That means the direction of current is towards west since the electron is traveling towards east. So you have got the direction of current and the magnetic field. What is asked to find out? Force. We have already learnt in the previous case study video that if you have to find the force, you should use Fleming's left hand rule. So take your left hand and point the forefinger and middle finger in such a way that the forefinger points downwards and the middle finger point towards the west. Note the direction of your thumb. It shows that the thumb is pointing towards the south direction. So the force experienced by the electron will be in the south direction. Second question. If a charged particle is moving along a magnetic field line, then what would be the magnetic force on the particle? Look at the second sentence of the case study. It is given that a charge moving in magnetic field will experience a force except when it is moving in a direction parallel to it. And in the question it is given that charged particle is moving along the magnetic field line. That means it is moving in the same direction of the magnetic field line, which means it is moving parallelly to the field line. So if the charged particle moves parallelly to the field line, that means the current and the field is parallel. Hence there will be no force experienced by the particle, or the force experienced is zero. Let's move on to the next sub-question. Sub-question C. A uniform magnetic field exists in the plane of paper pointing from left to right as shown in the figure. In the field, an electron and a proton move as shown. Where do the electron and the proton experience the force? So in this question also we are asked to find the direction of the force. That means we have to use Fleming's left hand rule. First let's find the force acting on the proton, because the direction of motion of proton and the direction of current is same. So take your left hand and release the forefinger towards the right direction and the middle finger facing upwards. Now release your thumb. What do you see? In which direction does the thumb points to? So you can see that the thumb points into the plane of the paper. Hence the proton experiences a force pointing into the plane of the paper. Now let's take the case of electron. When we take the case of electron, we should understand that the direction of the current is opposite to the direction of the flow of electron. So electron is going downwards, it means the current is going upwards. So again, according to left hand rule, we have the current moving upwards and the field moving towards right. So again, the force or the thumb is pointing inside the paper. That means the electron is also experiencing a force into the plane of the paper. Fourth sub-question, an electron beam enters a magnetic field at right angles to it as shown in the figure. What would be the direction of force acting on the electron beam? Again, take Fleming's left hand rule. The forefinger should be pointed towards right and the current will be in the upward direction because electron is coming in the downward direction. So the thumb will be moving inside the paper, that means into the plane of the paper. Hence electron is experiencing a force into the plane of the paper. Let's move on to the next case study. A current carrying wire produces magnetic field around it. The phenomena in which an electromotive force and current, if the conductor is in form of a closed circuit, is induced by changing magnetic field through it is called electromagnetic induction. The EMF so developed is called induced EMF and the current made to flow is called induced current. A student connects a coil of wire with a sensitive galvanometer as shown in the figure. He will observe the deflection in the galvanometer if the bar magnet is So according to the case study, we have understood that the galvanometer will show some deflection when there is an induced current produced. And to produce the induced current, the magnet should be either moved into the coil or moved away from the coil. Observe the deflection in the galvanometer when the magnet is moved inside and outside of the coil. So the answer is the magnet should be moved towards or away from the coil parallel to the axis of the coil. Second question, a conducting rod AB moves across two magnets as shown in the figure, and then the needle of galvanometer deflects momentarily. What is the name of this physical phenomenon? So let's understand that in order to produce an induced current, it's not necessary that always the magnet has to be moved. It can be the conductor moving in between the magnetic field. So here also an induced current is produced, and this phenomenon is known as electromagnetic induction. A bar magnet is pushed steadily into a long solenoid connected to a sensitive meter. What will you observe? Why? What will happen when the magnet is taken away from the coil? So beside you can see that when the magnet is moving into the coil, the galvanometer is showing some deflection. So the first part of this question can be answered as there is a momentary deflection in the galvanometer when the magnet is taken into the coil. Now, why is it happening? It is because when the magnet is taken into the coil, there is an induced current produced by the coil. So, the current is induced in the coil. That is why the galvanometer is showing some deflection. What will happen when the magnet is taken away from the coil? Observe the figure shown here. You can see that when the magnet is moving inside, the galvanometer is showing some deflection, and when the magnet is taken out from the coil, the magnet is showing some deflection but in the opposite direction. So there is a momentary deflection seen in the galvanometer in the opposite direction. And children, what do you think will happen if the magnet is held stationary inside the coil? Yes, there will be no deflection. Okay, moving on to the fourth question. An induced EMF is produced when a magnet is plunged into a coil. The strength of the current is independent of, so there are four options given here: number of turns, speed with which the magnet is moved, strength of the magnet, and resistivity of the material of the coil. When is an induced EMF produced in the coil? It is when the magnet moves in and out of the coil. That means it should be dependent with the speed with which the magnet is moved. So option B cannot be the answer. Children, what do you think will happen if you use a stronger magnet here? Yes, a stronger magnet may increase the induced current. So the strength of the magnet is also not the answer. And already we have studied that in a solenoid, when the number of turns of coil increases, the field increases. Similarly here also, when the number of turns of coil increases, it will increase the amount of induced current. This means that option A, B and C are not the answer for this question. Hence, induced EMF is independent of the resistivity of the material of the coil. So that's all for this video. I hope that you have understood both these case studies very well. Do check the channel for the last minute quick revision of the chapter Periodic Classification of Elements and Electricity, and all the best for your term 2 examination. If you feel that this video was helpful for your revision, do drop your comments and share the video among your friends. Also subscribe the channel for more content of class 10.